Hello guys, welcome back to my channel, and today we are going to be talking about process capability and process performance capability and what these terms exactly mean, how do we use it and when to use these terms, and the finer nuances associated with those terms. So as you can see, I have few terms written over here: Cp, Pp, Cpk and Ppk, and you would be able to see over here the formula for both Cp, Pp is essentially the same, and so is for Cpk and Ppk. So over here the formula is upper specification limit minus lower specification limit over 6 sigma. So as you can see, upper specification limit and lower specification limit is something that we want to define in our key characteristic. The limits that we want to define in our key characteristic for in our manufacturing process, which would affect the performance of our product and which would directly correlate with what customer is expecting from our product. So let us assume that we are manufacturing a gearbox and there's a shaft like this which has a keyway and supposed to engage two gears or two flywheels together. So the length of the shaft, essentially, if it's too little or too more than what is required, it's going to affect the performance of those two flywheels connected together. So we have a spec over here for 100 centimeters plus minus 5 centimeters, and we want our process to be 6 sigma or more or less than that, or whatever. Standard could be 1 sigma capable. Depending on the industry and depending on the company, these values vary. So first we need to identify the key parameter in our product, what would affect the mentality of the customer or what would directly correlate with the performance of the product and that the customer would notice. So I took that as an example. So over here, when we talk about the key difference between CP and PP is PP is for long-term process performance and CP is process capability. So with CP we are essentially saying, or this is an index which tells us how capable our process can be. PP is essentially something which says how well performing our process is right now. That's why it's called process performance index. So over here the difference, since the formula is same, the only difference between these two indices is how we calculate the standard deviation. So this is how we calculate the standard deviation for PP. And this is how we calculate for CP, a short-term performance. Now these values, this is the range and this is another constant that we get from the statistical charts. This is the standard deviation formula which we use when we know our process is stable and we already have that characteristics in the SPC control charts. So over a period of time we'll gather the data, and that's how we'll calculate the short-term process capability through this index using this standard deviation. The key aspect of this one is we would assume that within subgroup deviation is less than between subgroup deviation. Process performance capability would capture everything, like how the process is varying over shift, during daytime, during seasons, or with the team members. So things like that are encaptured through the PP index using this formula. Over here, this is the individual value, this is the mean value. So we subtract the individual value from the mean value, square it up, do the summation of each value, and then you have number of samples minus 1. That's how you calculate the standard deviation over here. And essentially the CPK and PPK value is something with what we calculate when the data is not centered, there is a shift. So if the histogram for that one is something like, I'll try to make it. So the mean is kind of shifted from the center. That means there is a process shift. Something's going wrong in the process. So we need to look at it like which is systematically shifting the recorded values from the mean. So this is when this thing happens. This is also characterized by another characteristic called as skewness. And when there is this wider spread of the data, as you can see in this green graph over here, that means our kurtosis is more, that is the spread is more. That's another index what we can use. So looking at this data, what we can say, like the first step should be to do gauge R&R for the measurement system that we are using, to ensure that whatever measurement system we are using, if we are using caliper to measure this distance or whatever, CMM, whatever measurement system that we are using to calculate our key parameter, does not have a error value of more than 20%. That's the usual standard. Each industry has its own different critical value. Some industries use 10%, some use 15, some even use 30. So depending on what you are manufacturing, what the product is, how critical the parameter could be to the performance or the safety of the customer, depending on that, those values can vary, and that's how we define the error percentage, the critical value of error that can be contributed through the measurement system. So for example, let's assume I'm measuring this thing through a caliper, and my caliper has an error percentage of more than 30%. That means there's a possibility that my measurements could vary between like up to 30 centimeters plus minus in 100 centimeters worth of length of a product. So that's too big of a measure, and especially when I have a tolerance limit of plus minus 5 or 10 on both sides. So that's a big contribution, and that can adversely affect our product and also our customers. So we wouldn't want that. So we would need to define the critical parameter or use the critical parameter what our industry has already defined for that particular characteristic. If it's 10%, 15% for gauge R&R value, we cannot have error percentage more than that. Once we have defined that, then we will measure like whenever we are qualifying a new machine, if there's a machine which is cutting the shaft into this spec, we would take 30 measurements, at least 30 measurements, I'd say. It depends on what is the production scale for that particular product during the day. Depending on that, we'll do 30 measurements, record the values, plot it on the histogram, and depending on that. So as you can see over here, this is the LSL, this is upper specification limit. So specification limit is essentially, which is voice of the customer, so 100 centimeters plus minus 5 centimeters. So we can say this is like minus 5 over here, and this is plus 5, or if this is, it should be USL over here. So I'm sorry about that, but so let's consider 5 over here and minus 5 over here. So it should be upper specification and upper control limit on that side and lower on this side. So I apologize for that mistake. Control limits are essentially how good our manufacturing process is compared to the specification limit. So if the customer demand is for 100 centimeter plus minus 5 centimeters of tolerance, and we say the machine can cut up to 3 centimeters of accuracy, like plus minus 3 centimeters, then that would be our control limit. Or we can call that as voice of the process, that our process is that much capable of doing that thing, and therefore I marked the upper and the lower control limits within those. Always in every industrial setting, you would want your control limits to be smaller than the specification limits. Never at the same size or bigger. Like, it's not wrong if it's of the same size, but it should not be, in most of the cases, same size as the specification limit. It should be smaller because you want your process to be more capable than what is required by the customer. So for example, if I measure 30 values and I plot it over here, I would calculate my process capability value using this value. So it could be plus and minus, so that could be 10 over standard deviation. So essentially what we are trying to see, if my machine, when it cuts and I'm measuring 30 of those measurements, if I can fit 12 standard deviations between the upper specification limit and the lower specification limit. Obviously I'll take 30 measurements. If the variation between each of those measurements is quite small, the standard deviation would go small. This value will be lower, obviously. If this value is lower, that means that I will be able to fit. This is nothing, because if you look at it, this can be, for this value to be 2, Cp value or Pp value to be 2 or 6 sigma, what we would want is between this range, we would want to fit 12 standard deviations. So if my standard deviation is low, like you can see, like usually you would have seen on Instagram, those are made like sections like this. This represents one standard deviation. So the narrower it is, more standard deviations we would be able to fit within these specification limits. And it could be 2, higher than 2. So essentially we have 6 standard deviations. Even if we keep it like that, and we have this value which is like 10 or whatever, and standard deviation comes out to be, if this value, for example, upper specification limit, lower specification limit comes out to be, for example, just making up a number, comes out to be 12 and standard deviation is 1, that means we are able to fit like that process 2 times within the specification limits. That's how good our process is. Another key point to remember is we will always calculate the standard or the process capability with respect to the specification limits, not the control limits. That's the key point to remember. So first step, we need to do the gauge RNR before qualifying the machine to make sure that there is not too much of an error in the measurement system. How we are, like once we are cutting the shaft, measuring it, so the device that we are using, the measurement system that we are using to measure that length does not contribute to error more than 20%. So 20% is an example in this particular case. And so given that we know that, and then we'll calculate our process capability. So when we are qualifying the machine, we would be calculating PP because we have 30 measurements. First we'll do 30 measurements, then we'll calculate our process capability. If it's not centered, we'll use that value, which is upper specification limit minus the mean value over 3 standard deviations, or mean value minus lower specification limit over 3 standard deviations. So whichever is lower, we'll use that, because if it's away from it, it will have a bigger distance from the lower control limit compared to the upper control limit, specification limit, I'm sorry. So we would want the minimum value to be considered as the process capability value. So for qualifying the machine, we'll always use PP. Once the machine is qualified, we have identified the key parameter. We would want to implement the SPC chart for that particular parameter. That's important because implementing SPC for a particular parameter is not cheap, so we have to be very mindful of which parameter we are thinking or trying to implement the SPC on, because that's going to cost a lot of money to the company. So we need to make sure about that. Once we have done that, then depending on the process, criticality of the process and the industry, we would need to do the process performance capability, like after a while, 6 months, 3 months, whatever it may be, which is CP, and we'll use this formula for calculating the standard deviation in this case, which would tell us this is the short-term capability of our process. This is the long-term capability, this is the short-term capability. So I hope you guys have cleared your concepts as far as process capability and other related topics on this one. Please let me know if you have any questions in comment section down below, and I'll see you all in the next video. See you.